Hey guys, Professor Doney back. We're in the middle of doing some problems. Now we're talking about buoyancy and the force, or the buoyant force. Okay, and buoyant force is something that buoys or lifts up, and it's typically a force that acts on an object when it's in a fluid. Now, since we are, or I hope you are, we're in the middle of fluid, meaning air, we would have a buoyant force right now in air, but we really don't feel the effect until we go into something much denser like water. Okay, that's where we really feel a buoyant force. That's why it feels so nice to sort of float around in the pool and to move things in a pool. It also is why fish don't seem that heavy and don't break your line until you try to lift them out of the water. All of a sudden they appear to become heavier, and all of a sudden your line snaps when you're pulling them out. So let's look at this example here. We have some sort of cube here, or some sort of box or bar. Measures 0.2, 0.2, 0.4 meters, length, width, height, and we're told the density is 2,000. So let's find a whole bunch of things about it. What is the weight of the object? Now, when we say the weight of the object, we pretty much are assuming or implying that it's the weight in air we put on the scale. That's mass times gravity. Since we don't know the mass technically, what we're going to do is take this, we're going to go back to the density equation, mass per unit volume, and we're going to rewrite that as mass is density times volume. Okay, so we're going to use that down here. So that's going to be density times volume times gravity, which looks very close to this buoyant force, but we'll come back to that. So what do we have here? 2,000 times the volume, which is going to be 0.2 times 0.2 times 0.4 times 9.8. Boy, the handwriting is really falling down here. All right, 2,000 times 0.2 times 0.2 times 0.4 times 9.8. I get 313.6, and that would be newtons. All right, that's what the object weighs in air. Now, what if we go through and say, all right, we're going to put it in water. What does it weigh in water? Okay, so we're basically finding the weight underwater. We can call it that. Well, when we put something underwater, it still is going to have its weight down. That's the 313.6 we just found. All right. But we're going to see there's this buoyant force that makes it appear lighter. So what we're really trying to find out here is if we hang this from a scale underwater, what is that going to read for us? We know if we hang it here, just in air, it's going to read this 313. But what does it weigh underwater? So what we need to do, if we look at the forces, we end up saying we sum the force in the y direction equal to 0. We have the force of tension up, which is what it weighs in water, plus the buoyant force minus its weight in air, has to equal 0. Tells us the force of tension, which is what it's going to weigh underwater, is the weight in air minus this buoyant force. So let's find out what that buoyant force really is real quick. So how are we going to calculate? Well, buoyant force, as we see from the equation here, the big pink circle, is the density of fluid, so let's say it's in water, times the volume of the object, which is the 0.2 times 0.2 times 0.4 times gravity. So if I go through and do that, 0.2 times 0.2 times 0.4 times 123 times 9.8 tells 156.8. Now what that means is the buoyant force up is basically what we subtract from there. So what we're going to end up having is that force of tension, which is the weight underwater, is the 313.6 minus 156.8. If I did that right, well, is that half? Really? Wow, it came up to be half. 156.8 newtons. So underwater it's going to weigh that much, half as much. Real quick there, hopefully I did the math all right. If not, I'm sure you'll tell me, and we'll see you in the next video.